Welcome to Empowered Learning. This video will be about the comparison test for series. And so specifically, what we are going to talk about is a test that we can use to be able to see if a particular series converges or not. And the two tests that we're going to talk about is the basic comparison test and also the limit comparison test. Now, these tests, if you are, let's say, in a second year calculus course, you've kind of already seen these tests before, but you've seen them expressed in terms of improper integrals and not necessarily in terms of series. So right now we are trying to essentially figure out, do we have some series that will notate like this in short? We want to know if some series like this is going to converge or not. Okay. Now, of course, if we put some extra notation on it, usually we'll have the summation going from n equals 1 or some other integer on to infinity, and it'll look like this. And so the thing that we need to realize here is that a series is just, we're just adding up a bunch of numbers in a sequence. And this sequence here is actually a function, whereas domain is just natural numbers. And so the behavior of this series is actually going to mimic the behavior of this particular improper integral here. So I'm going to write it. So if we had some improper integral here, and let's say a sub n was going to be a function of n, then here we know that the function f of n will mimic the behavior of the function f of x. So the point that I'm trying to make here is that this particular series here will behave in the similar fashion as this improper integral here. Okay? And so the point I'm trying to make is that when you went over the direct comparison test for improper integrals and the limit comparison test for improper integrals, the things that were stated there are pretty much what we're going to state here. But since we're dealing specifically with series, we're going to drill down and be a little bit more specific on what the outcomes are. Okay, so I'm going to go back here momentarily to the direct comparison test and limit comparison test for improper integrals so that you can see that. And then afterwards, when we cover what the comparison test and limit comparison test are for series, you're going to see the similarities there. So if you watch my video on improper integrals, then you've already seen this before, but I want to do this as a quick review. So we have a direct comparison theorem for improper integrals. And suppose that we have two functions, f and g, they're continuous. And we know that both f and g are going to be positive or non-negative, I should say here. And of course, my function f is going to be a function that's bigger than my function g here. Okay. So, and we're just going to deal with this situation for now. Okay. Now we can also deal with number 2, but in terms of how we deal with the series, this number 2 condition won't necessarily apply. So here, if we look at condition number 1, what we basically know from the direct comparison test for improper integrals is that if this is the larger function, then the improper integral of the larger function, if it's convergent, then it means that the improper integral for the smaller function is also going to be convergent. Okay. We also know that if we're dealing with the smaller function and we evaluate that improper integral, then if it diverges, meaning that the improper integral for the smaller function diverges, then that means that the improper integral for the larger one will follow suit. Okay. It will also diverge. And so with the direct comparison test for improper integrals, is very specific. If we have the larger function and we know that that improper integral converges, then we can say the smaller one does as well. And if the smaller one diverges, then that means that the larger one will diverge as well. So the issue here is that, and of course I have some old info from the video that I recorded there. The issue here is we have a situation where, let's say that, and I'll go back here for a second. Let's say that we're dealing with the larger function, but instead of it being convergent, it's divergent, okay? Or we're dealing with the smaller function here and it's convergent instead of divergent there, okay? So when we have these situations, we can't use a direct comparison test, okay? We also have a situation where if, let's say, the g of x is the larger function and the f of x is the smaller one, then of course, if we switch these situations here, that's also going to nullify us using a direct comparison test, okay? So in that sense, we have to use the limit comparison test, and that's what this information here is all about. And I'll clear this out so that we can read it. So for the limit comparison test for improper integrals, we see that if we have two functions that are both continuous on some interval from some value a to infinity, both of them are considered to be non-negative. And of course, we don't have the condition anymore where f of x has to be a function that's bigger than g of x. So we're not worried about that. So if both of them are just above or on the x-axis here, and if the limit of the quotient of those functions is equal to some real number value L, which we're considering here to be some positive value, then we know that either both the improper integral for the larger function and for the smaller one will both either converge or both diverge. And so again, it really doesn't matter which one's the smaller or the larger one. If it meets this condition of both functions being non-negative and the limit of the quotient of f over g, or we can say g over f, is going to be equal to some real number that is positive, then essentially what we know here in this case is that both improper integrals are going to pretty much act the same, okay? Now, again, the point of me bringing this up before we actually start covering the comparison test for series is that the language that we see here for both the comparison test and limit comparison test are going to be very similar, okay? So if you're comfortable with knowing the direct comparison test and the limit comparison test for improper integrals, then you're going to be comfortable with dealing with the comparison test and limit comparison test for series because they're very similar. So now that we've seen the direct comparison test and limit comparison test for improper integrals, now let's go ahead and look at what the comparison test and limit comparison test look like for series. So the comparison test says that suppose that we have two series, and so we have the series that is made up from a sequence a sub n and another series that's made up from a sequence b sub n, okay? Both of these series, in other words, both of the sequences are going to have all positive terms, so that means that the corresponding terms of the sequence are also going to be positive as well for all values of n, meaning natural numbers, greater than or equal to 1. So if we have two series that meet both of these conditions, then we know that if we have a situation here where if this series b sub n is convergent and we know that the sequence a sub n is less than or equal to b sub n, or if we put this another way, if the series that is bigger is convergent, and I'm saying bigger because the corresponding sequence is bigger than the other. So if we have a series, the bigger series is convergent for all values of n greater than or equal to 1, then that means that the smaller series is going to follow suit and also be convergent, okay? So I'll say that again. if we have a situation where we have two sequences where B sub n is the bigger sequence, A sub n is the smaller sequence, and they both make up these corresponding series, which means this series with B sub n is going to be bigger than the series with A sub n. If we have that, and of course, A sub n and B sub n have all positive values, then here, if our bigger series, if it's known to be convergent, then we know that the smaller series will also follow suit and be convergent, okay? Now, if we have a situation where we have a series, and let's say in this case, the B sub n is the smaller series. And so that's what this part means. Because in this case, B sub n is going to be the smaller sequence. So that means that this is going to be the smaller series. So if this series is the smaller one and it's divergent, then that means that the corresponding larger series will also be divergent, okay? And notice that that language it sounds very similar to the direct comparison test for improper intervals, okay? Now, note number one is here we know that for this particular situation with 1i, we know that if B sub n is bigger than A sub n, and this corresponding series is known to converge, then we know that the small series is also convergent. But if we have a situation where we know that this particular series converges, but it is the smaller series, it's the smaller sequence here, which means that this is going to be the smaller series, then the comparison test can't be used, okay? So for instance, notice here that the point that I'm trying to make is that here, let me put this in back there. If we notice here that whenever we have a situation where the series is convergent, we know that B sub n has to be greater than A sub n. And notice here that that's not true, okay? So we have a situation here that is not the same as what I was talking about up here, okay? So because of that, I can't use the comparison test in this situation, okay? And so we'll have to use another type of test, and that's where the limit comparison test will come into play, okay? Now, note number two addresses our situation with 2i. So if we have a situation where we're dealing with a series that is divergent, but the A sub n sequence is smaller than the B sub n sequence, which of course that is not the same as what I have here, then of course I can't use the comparison test for this situation. So again, for these two situations in particular, we are going to have to use another way of trying to figure out whether the series that we're dealing with converges or not, okay? And so note number three just says that if we get at least one of the two conditions explained in notes 1 or 2 above, that's going to disqualify us for using the comparison test. But the good thing is that we can use the limit comparison test for series as well. And so that's what we're going to talk about next. So the limit comparison test says that suppose we got a situation where we're dealing with two series, and of course the sequences A sub n and B sub n are the originating sequences that form these series, okay? And of course A sub n and B sub n both have positive terms just like before. Then if they meet that condition, if we do the limit of A sub n divided by B sub n, and it equals to some real number C, okay? And based upon what C looks like, we're going to have different outcomes. But if we get some value C here, then depending upon what it is, it's going to tell us what the convergence properties are, okay? So again, here we basically have two series, and we know that both of those, the corresponding sequences of the series have positive terms. For all of them, for all values of n greater than 1. And we know that when we evaluate this limit here, we get some outcome. Now, if the outcome is going to be a real number value C that is positive, then this reads very much like the direct comparison test for the for improper integrals, which is in this case, either both of these series will converge or both of these series will diverge. And again, let's say we know that in this case, our B sub n converges, so that means A sub n will follow. Okay. If we have this same situation, but let's say we know our B sub n diverges, then that means A sub n is going to follow. Okay. Now, if C is equal to 0, then what that's communicating to us is that our B sub n sequence is indeed growing faster, or put another way, it is bigger than our A sub n sequence as n approaches infinity. So in other words, the B sub n function grows faster than the A sub n, okay? And so in that situation, since B sub n is the bigger sequence, then of course the corresponding series summation of B sub n will be the bigger series. And if the bigger series converges, just like what we know from the direct comparison test for improper integrals, then the smaller series will also converge. Okay. Now, the flip side of that is that let's say this value C here ends up being an infinity. I put plus or minus infinity, but if all of our terms or values from A sub n and B sub n are positive, we're just going to see the infinity case, but I tried to do a catch-all here. So just focusing on the infinity part, if we see that this limit equals to infinity, then what that means is that our A sub n sequence is the larger of the two sequences here. So this is the larger sequence, that's the smaller sequence. And so here, because of that, if our smaller sequence corresponds to this smaller series, if it diverges, then that means that the bigger sequence will also diverge. Again, similar language to the direct comparison test for improper integrals. Okay, so test or just number 4 here says that this test will be inconclusive if it doesn't meet one of these earlier 3 conditions here. Okay, and so specifically speaking, if C is equal to 0, kind of like how we have here, but we know that our series here, the bigger series, it diverges. So this is one condition where if we have this situation, limit comparison test is not going to help us. Okay. The other condition is if C ends up being, positive or negative infinity, but instead of this particular series here, the smaller series diverging, we know that the smaller series converges. And so, of course, in that situation, we can't use a limit comparison test. So that is the limits that we have on that. Okay, no pun intended there. So what we're going to do now is, now that we've kind of unpacked what the comparison test and the limit comparison tests are and how we can use them as well as their limitations, we're going to do several examples to try to get you comfortable with being able to figure out what to use and how. Okay. Okay, so we want to determine if the following series that we're going to see here are going to be convergent or divergent. It is suggested that we use the comparison test first, if possible. If the comparison test can't be used, then we want to use the limit comparison test, if possible. I'm going to also throw in here, if we recognize that the type of series that we're dealing with is going to be either a geometric series or a harmonic series, then we're just going to go ahead and state the fact that, hey, we're dealing with a geo series or a harmonic series, and from that we'll be able to know whether that particular series will converge or diverge or not. Okay, and so we're going to use these two types of series here as leverage in trying to do these problems. Okay. All right. So let's look at this first example to kind of get an idea of how this is going to work. So here, what I'm going to do and this is just for the sake of simplicity here, whatever series is given to us, the function that makes up the series, of course, is the sequence, and I'm always going to call that the a sub n, okay? So here I'm going to let a sub n be this actual series here. Now, b sub n, we want to select b sub n in such a way to where it's very similar to, it's going to have the same kind of behavior as the a sub n, but it's going to be easier for us to deal with. And so in this case, if I was to ignore this plus 7 here and let b sub n equal just 1 over 8 n squared, then I know that 1 over 8 n squared is going to act very similar to 1 over 8 n squared plus 7. Okay? Now, in this case, the only thing that's really different here is that because I have this plus 7, this denominator is going to be bigger than the denominator of just 8n squared. And thus, what that means is, hey, if I'm taking 1 and dividing it by, let's say, 3 versus 1 dividing it by 2, I know that 1/2 is going to be a bigger number than 1/3. So because of that, what that tells me here is that my a sub n is going to be smaller than my b sub n, okay? So now I have two sequences that I'm comparing to each other, and I know that the a sub n sequence is smaller than the b sub n sequence. So what that also tells me is that I have two series to compare, mainly the series with a sub n and the series with b sub n, okay? Where the b sub n one is going to be known as the bigger series. The a sub n one is going to be known as the smaller series, okay? And so since b sub n is the bigger series, according to the comparison test for series, we know that if this bigger series is convergent, then that's going to imply that the smaller series is also convergent, okay? So what we need to do is hopefully show that our bigger series is actually a series that converges, okay? Now, if you notice here, if we go ahead and write all this out, then notice that what we're actually dealing with here is a p series, okay? And if you watch my videos on the integral test, one of the things that I talked about in that video is what the p series was and how we knew whether that particular series is going to be convergent based upon what p is. So here, I know that this is going to look something like this. And I know I could factor out a 1/8, so I'm going to go ahead and do that now to make this look a little bit easier here. So we got this equals, and we have this, okay? And so this is a p series. Let's make that look a little better. So it's going to be a p series. I'm going to write out what that is. So we got a p series, which looks something like this. Where p in this case is greater than 1, okay? And so we know that for a p series, and I'm using it with x here because that's how we originally saw it, but since we are dealing with series now, we're going to let that actually be n, meaning natural numbers here. So our p is equal to 2, which is greater than 1. And we know that p series converge whenever the value of p is greater than 1, okay? So therefore, P series converges. Because P is 2, which is greater than 1. Okay. So because of that, what we know as a result is that this particular series here will also converge. Okay. We know it converges because, again, it's just 1/8 times a P series. Okay. And so we know that this particular series converges. So therefore, this in its original form will converge. And so since this is the bigger series, then that means, and I'll kind of write this here. So since this one converges and it's the bigger series, then what that means is this one also converges because it's the smaller series. And remember, if we have a situation where our A sub n and B sub n values are all positive and the corresponding series of the bigger sequence converges, then that means that the smaller sequence, well, the smaller series will also converge as well. Okay. So therefore, our answer to this is that this particular series will converge and this is via the comparison test. Okay. And my T didn't come out that well, but all right, so we got the point there. And so this is what we will be doing for all the examples that we do in this video. Okay. It's just looking at what you have, saying, well, if I chop off some things, but yet it'll still act the same, meaning the sequence that I'm dealing with, then I just come up with a comparative sequence, form a series out of it, and then compare which one says, all right, well, which sequence is bigger than the other? And then, we just follow the rules for the for the comparison test. Okay. And of course, if it doesn't meet the conditions for the comparison test, then we try to do the limit comparison test. All right, so let's look at our next example and see if we can gain a little bit more traction here. Okay, so for this second example, kind of the same thing. We want to start off by identifying what our A sub n is going to be. And this is just going to be the actual sequence that that forms this particular series itself. Okay. And so for our B sub n, what we're going to do is chop off like this +6, this +1, and this +2 here. Okay. So if we chop that off, we'll just have 9n over n times n times n, which of course will just be n cubed. And of course, one of these n's will reduce to 1 with the other. So what we'll have left here is 9 divided by n squared. Okay. So if we look at this, we know that because we have the +1 here and the +2 there, the denominator for n cubed is going to be smaller than the denominator for n times n plus 1 plus times n plus 2. So because of that, what we know is that since A sub n will have a bigger denominator, it will be a smaller value for larger values of n that we plug in. So essentially what this tells us is that, again, A sub n is going to be smaller than B sub n, okay? And so what this also tells me is that my series A sub n is going to be the smaller series out of B sub n, okay? Now, we look at this and this is the corresponding sequence for the series that we're trying to figure out. But here is the series that we want to use. Again, this looks like another P series, right? So we have this, we got 9 over n squared here. So this is just 9 times summation n equals 1 here. And of course, this is a P series where P is equal to 2 again, which is greater than 1. So therefore, this particular series will converge, and that implies that my series for what I was originally considering here is also going to converge, because remember, the original series relates back to this a sub n sequence, which is the smaller one out of the two. Okay, and remember, if the bigger series converges, then the smaller series follows suit and converges via the comparison test. Okay, and that's all there is to it. So we're going to go ahead and move on to the next example, but hopefully now you're starting to see how we analyze these series to be able to get a comparison sequence to form a series out of that, and then use that to help us figure out if it's going to converge or not. Okay. All right, so for our next example here, and I'm going to make sure that this is clear because all of this is inside the summation operator. So we have this series where the corresponding sequence for it is n divided by 5n plus 6, all that raised to the n. Okay, so in this sense, of course, our a sub n again will just be n divided by 5n plus 6, all that raised to the n. The corresponding b sub n for this will chop off that plus 6 there, and we'll just say that this is n over 5n, all that raised to the n. And of course, we know that these n's here would reduce to 1, and all that we'll have left there is a 1/5, all that raised to the n. Okay. So if we consider the series here, where we have 1/5 raised to the n, notice that this particular series looks very similar to a geometric series. Okay, the only thing that's different here is that we would normally have an n minus 1 here instead of an n, and so we can easily fix that by rewriting 1/5 raised to the n as just 1/5 times 1/5 raised to the n minus 1. Okay, and so we know from this is a geometric series where our a is going to be 1/5, and our r is also going to be the same thing in this case. Okay, we know that because this is where our a is, that is where our r is. Okay. So because of this, we know that this particular series is going to converge. We'll say this series converges because we know that r, which is 1/5, is within the interval of -1 to 1. So in other words, 1/5 is in between -1 to 1. So we know that it's a geometric series that converges. Okay, so therefore, because of that, we know that in this case, and I forgot to write this, but here our b sub n sequence is going to be larger than the a sub n sequence, just by sheer fact that the denominator here is larger. So that means that the numbers are going to be small, that the total number that we get for the sequence a sub n is going to be smaller. Granted, everything else is the same. So because of this, the corresponding series that goes with this particular sequence is going to be the larger series. And since the larger series was convergent, then it means that the smaller series will also be convergent. Okay, so therefore we can just say that this particular series here will also be convergent. And that is because of the comparison test again. Okay. All right, let's move on to the next example. All right, so for this particular series here, again, we know that since we're dealing with values from n to infinity, that our numerator and denominator will both have all positive values. So, well, I should say non-negative values in this case. But here, we know that if we compare this, it's going to basically work for us to try to use the comparison test. Okay, so our a sub n, the sequence that actually forms a series in the first place, we'll just go ahead and identify that. So that will just be this squared divided by n cubed. And so our b sub n is something that we want that looks similar to this or behaves similar to it, but is not going to be, exactly the same. Okay. So in this case, we don't have anything that we can trim in the numerator and denominator here. But one thing that we do know is that this natural log function here, of course, a natural log function, it looks like this. Okay. And so because of that, we see that as n or x gets more positive, it's going to grow, but it's going to grow or increase very slowly. Okay. So at first glance, one of the things that we could probably do, and you're going to see why we probably shouldn't do this, but you probably need to go through this one time just to realize it for yourself, is that b sub n, we would probably want to say, well, let's just let this be 1 over n cubed. Okay. And so at first glance, we're like, yeah, that will be good. However, you got to think about, in this case here, we know that the a sub n function or a sub n sequence is eventually going to be larger than the b sub n. Okay. Now, how do I know that? Well, if we're just comparing natural log of n to 1, if I draw a graph of that, this will be y equals 1. Okay. And let's say we draw a natural log function, it's going to look like this. And the exact place where natural log of n equals 1 will be right here. And that is that famous irrational value of e, which is approximately 2.71. So here, what this means that in terms of natural numbers, for all values of n 3 and higher, our a sub n function is going to be a bigger function or sequence than the b sub n. Okay. So here, if we go that route and say, all right, I just want to use this, then I have to look at this b sub n as the smaller function. Okay. And so if I look at the b sub n as the smaller function, then what I'm hoping for is that the corresponding series that goes with the smaller sequence function is going to diverge. Okay. Now, quick analysis of that will let you know that, nope, this is not going to work well for us. Okay. Because if I look at this particular series here, this looks like a p series where p is equal to 3, which is greater than 1. So what that means is that this series will converge. However, if b sub n is my smaller sequence, I'm hoping that the corresponding series for that will diverge, not converge. Okay, because that's what the comparison test told me. So right now I'm in a situation where I have A sub n is larger than B sub n, but this particular series here converges. I can't use the comparison test for this situation. So I would have to use the limit comparison test to be able to work this out. Okay. And so the limit comparison test would say I would have to do the limit as n approaches infinity of A sub n over B sub n, which essentially would just be natural log of n squared here divided by n cubed all over the reciprocal of 1 over n cubed, which would just be n cubed here, okay? And of course, this would end up reducing to 1. And if I keep working this out here, I just have this situation here. And because this is a composition function, and I know that anything squared will actually be a defined value, I would have to go and now move my limit operator on the inside. So I would have to look at it like this, okay? And of course, we know that natural log of infinity, when I plug in n for infinity, will be infinity. And of course, infinity squared is infinity. So I have a situation where all of this is just equal to infinity, okay? So what that tells me here, in terms of limit as n approaches infinity of A sub n over B sub n, since this result ends up equaling infinity, then that means my A sub n function or sequence is the larger one out of the two, okay? Again, I have a problem here because of the fact that if I go back to the limit comparison test, when I have this situation where I have infinity, whenever I do the limit, I am hoping that I know something about the smaller function. And in particular, I'm hoping that the smaller sequence in this corresponding series diverges, okay? So the point that I'm making in this example here is that by me choosing the wrong, or I shouldn't say the wrong, but choosing a B sub n sequence that doesn't really help me out a lot, I've just basically did a lot of work and I still haven't gotten anywhere, okay? Now, there are other tests that could help us out here, but we're not at that point. So what we could do instead is, instead of using 1 divided by n cubed here, and of course, it's attractive for us to want this B sub n to be the larger sequence, we could change this and say, all right, well, instead of having n cubed, how about just n squared in the denominator, okay? So if we do n squared in the denominator, well, I know that any 1 divided by n squared will definitely be a larger number than, let's say, 1 divided by n cubed, okay? And here, it turns out that 1 over n squared is always going to be a value larger than natural log of n squared divided by n cubed. And I'm going to erase some of this work here and actually show you why that is. All right, so here what I'm proposing is that A sub n is larger than B sub n here, which means that this natural log of n squared over n cubed is going to be larger than 1 over n squared, okay? Now if we go back to arithmetic for a second, one of the ways that we could determine if a particular number was larger or smaller than the other is we could do some cross multiplication here. So I am going to get rid of the sign for just a second and just say, all right, well, what is this? Well, if we did cross multiplication here, going here and going here, then what we would end up with is n squared times natural log of n quantity squared. And on this side, we will have n cubed, okay? Now, if you notice this, this is going to be, and I'm going to rewrite n cubed as n times n squared, okay? Okay, so if we look at it this way, we see that the n squareds kind of nullify each other here. And so the only thing that we're really comparing here is n and natural log of n squared, okay? Now, if we looked at a graph of natural log of n and then squared it, what that's going to look like is essentially a natural log function, right? So it's just going to look like that. If I was to graph y equals n, and really I'm thinking about this as, let me just say this, I'm thinking about it more so as natural log of x squared in x here, okay? And so this blue graph represents natural log of x, and then we square that. So if we look at, let's say y equals x, that graph is going to look like this. And notice that my brown graph for y equals x is always going to be larger than natural log of x squared, okay? So for that reason, we know that n is always going to be greater than natural log of n squared. So that's why I can actually make that statement there, okay? And so for these problems, the hard part is trying to figure out what is a good b sub n to use here, okay? And so that's why I'm able to say that. So now that we know that our a sub n, the sequence for the original series that we're considering, is the smaller of the two, and now I know my b sub n is something that I can use, again, I know that this b sub n, if I use it in a series here, this is going to be a p series, okay, where p is equal to 2, which is greater than 1. So I know that this particular series will converge. Therefore, I know that the series that I've been considering the whole time, I know that since this is the larger series and it converges, and that means that the smaller series will also follow suit and converge as well. And that's going to be via comparison test. Okay. All right. So I know that one took a while, but I had to kind of go through the process of making a mistake and showing you how we realized we made a mistake in choosing the b sub n sequence to compare before we could actually choose the correct one. Okay. So for our next example here, we have this series, and of course, it does check all the boxes as far as these values 1 and whatever the denominator is, both having positive values. We know here that by default, our a sub n is just going to be whatever the sequence is that forms this series in the first place, okay? Our b sub n, in this case, we're just going to chop off that -1 there, and we'll just say this is 1 divided by n times square root of n squared. And of course, since n is going to be values that are 2 or higher, we know that square root of n squared is actually absolute value of n, but since n is always going to be positive, I can just assume that that's n as well, and we can look at this as n squared, okay? So again, we have a situation where we're looking at this, and in this case, since I have this -1 here, and here I just have n times square root of n squared, the a sub n function is going to be, or a sub n sequence is going to be the bigger one this time, okay? So since the a sub n is going to be the bigger one, I am hoping that the b sub n sequence relates to a series that diverges, okay? So that's what I'm hoping for. However, if I look at this, I know that the b sub n, if I was to replace this, I know it looks like a p series, okay? So I know that it's a p series where p is greater than 1, so I know it's not going to diverge. So I'm in a situation where I can't use the comparison test. So what I'm going to have to do is consider the limit comparison test in that case. So here, comparison test. So it does not work. So what we want to do now is use the limit comparison test. So we're going to basically take the limit of a sub n over b sub n and see what that gives us. So my a sub n, of course, is just 1 divided by n times square root of n squared minus 1. And that's going to be basically multiplied by the reciprocal of b sub n, okay? And in this case, reciprocal of 1 over n squared is just n squared. So if we look at it that way, then of course this n and one of these n's will reduce to 1. And what I have left is limit as n approaches infinity of n over square root of n squared minus 1. Okay. Now, for me to be able to evaluate this limit, I'm going to have to do a little fancy footwork here. There's a couple of different approaches I could take. Probably the most straightforward approach, which I'm not going to do here, will be by using L'Hopital's rule, okay? And so the reason why I'm not going to use that approach is that if I take the derivative of the numerator and denominator, I'm going to have to do a little work here in taking the derivative of the denominator to figure out what that's going to be to evaluate it. To me, a much more slick way to do this is to realize that n can be rewritten as square root of n squared, okay? And because of that, whenever I have square root of something divided by square root of something else, here I know that I could rewrite what I have inside my limit operator as just big square root of n squared divided by n squared minus 1, okay? And if I look at it this way, it's going to be a lot easier to be able to evaluate this limit here. And I'm going to do less thinking in doing it, okay? All right, so here I have limit of square root of that rational function. And so here, because of the fact that this is a composition function here, one of the things I'm allowed to do is slide my limit operator on the inside part of this composition function, okay? Now, one of the things that we note here is that we are essentially taking the limit of a rational function where the degree of the numerator and denominator are the same. And of course, we could do some more fancy footwork here, but we know from pre-cal that this rational function n squared divided by n squared minus 1 is going to have a horizontal asymptote, and it's going to have it at y equals 1, because whenever we have degree of numerator and denominator the same, we just divide the leading coefficients by each other, and that's what the horizontal asymptote will be. And in terms of calculus, what that's telling us is what the limit of this will be, okay? So I'm going to erase that here. I'm going to do that in a different color here. So this is understood 1, that's understood 1. And so here, the limit of all of this is just 1. And so because of that, what I have is just square root of 1, which is 1. Okay. And so here, I notice that this is a value that is greater than 0. Okay. Now, using, according to the limit comparison test, so limit comparison test, I'm just going to write it as LCT. Says that because we have 1, which is greater than 0, as a result of the limit, this implies that both the series a sub n and b sub n, either they're both going to converge or they're both going to diverge. Okay. Okay. And so we already know, if we go back up here, that this particular series here, which is compared to the b sub n one, so remember this is what the b sub n was, since this particular series here converges because it is a p series where p is greater than 1, then since this converges, then we know that our corresponding series with a sub n will also converge. Okay. So here we're going to say, therefore, since this series with b sub n, which is going to look like this, converges, this means that the series with the a sub n also converges. And thus, our final answer for this is that this particular series here converges because of the limit comparison test. Okay. All right, so let's look at another example. Okay, so for this example, we see that we actually have a 2-term numerator here. So what I could do is rewrite this particular series this way. So we could rewrite it this way. And if I do some simplification here, I know that this will reduce to 1. And here, oh, that's 5. Yep, I wrote that wrong. So let me fix that. This should be 5 times n. So this should also reduce as well. So now that we have that, I can rewrite this as summation n equals 1 to infinity. And this is just going to be 1 divided by n minus 5 times 1 over 3 raised to the n. Okay. And of course, from here, I know that from my summation properties, I could rewrite this as 2 separate summations. Okay. And so if I go one step further here, and I don't necessarily have to do this, but I'm doing it just for clarity, I realize that this second term here could actually be written in geometric series form. And I can do that because I would need an n minus 1 there. So what I would have to do in this case is do the 1/3 times 1/3 raised to the n minus 1. And I would have that. So here, what we see is that this is the harmonic series. And here, this is 5 times a geometric series. Okay. Now, notice that the harmonic series diverges in all cases. This particular geometric series, it converges because R in this case is 1/3. Okay. So what we have here is basically the difference of two series where one diverges, one converges. And because of the fact that one diverges, and that means that the entire series is going to diverge. Okay. So here, therefore, our entire series is going to diverge because of the harmonic series part. Okay, and I'm just going to say because of that. And so that will easily let us know that for this particular series is going to diverge, and there's nothing else more we can do with it. Okay, so for our last example here, again, we want to pick our a sub n to be what the actual original sequence was here. And so I'm just going to keep it in this form. The b sub n, what we're going to do here is we'll just chop off that +1 in the numerator. In the denominator here, I have this times that. And so I know that the for values of n that are going to get more and more positive, the n squared is going to dominate over the 4n. And in that case here, I could look at this as just n squared times 6n. Okay. And of course, if I reduce here, then essentially what I have is a 1/6n squared there. Okay. So I know that a comparative b sub n sequence will just be 1/6n squared. Now, if I look here, I know that since I have more stuff in the denominator for the a sub n than the b sub n here, I know that the b sub n is going to be larger, okay? Because bigger denominator is essentially going to mean smaller number, whereas smaller denominator is essentially going to mean large number in this case. So therefore, I know that my a sub n here is going to be smaller than my b sub n. So what I hope for is that the series with the b sub n converges, okay? Because if the larger series converges, and that means that the smaller will follow suit. So here, I know that if I consider this particular series, then it's just going to be 1/6n squared here, which is just like saying 1/6 times this particular series here. And again, this is a p series where p is equal to 2, okay, and which is greater than 1. So therefore, this particular series, the bigger series converges. So that means that the smaller series also converges. So that means that this series here, it is going to converge by the comparison test. Okay. All right. So this concludes the examples that I have for this particular video. I hope that these examples kind of give you an idea of how to use the comparison test as well as the limit comparison test for series, And I also hope that I was able to sort of illustrate to you how the direct comparison test and limit comparison test for improper integrals is essentially the same thing that we're doing here. It's just that we get a little bit more specific with what the outcomes are, and we kind of outline some of the conditions to say, well, hey, if we have this and this, then it works. If we don't have this or that, then it doesn't work. And so we have to try something else. So hopefully I was able to communicate that in this video. So again, that is all. I hope to see you in the next video that I make that will be on alternating series as well as the ratio and root test. Take care.